Okay. Is it? Yeah. Okay, so you guys can see my screen, right?
Yes, sir.
Yes, sir.
Okay. Right, so today we're going to discuss the last DPP of magnetic effects of current, which is basically the force acting on a current carrying wire. So most basic formula that we have over here is when you have a magnetic field like this, and you have a, let's say, a current carrying wire, it has a current I, you want to find out the force acting on that wire, right? So we know that F bar is equal to Q into V bar cross V bar. That is a force acting on a moving charge placed on a magnetic field. Now, a current carrying wire is nothing but a collection of moving charges. So if you find out the force acting on each of the charge that is moving inside a wire and you add it up, you will get the net force acting on the wire. Okay. And if you do that, you're going to end up getting this formula. Okay. So if you take a small element over here, which is having a length given by the vector dl bar, and the direction of dl bar is in the direction of current. Now, if you find out the force acting on it, it will end up being this I into dl bar cross b bar. Now, based on this, we have a very common case where you'll have two infinite wires, and you're supposed to find out the force acting per unit length between the two wires. So this is I1, let's say, this is I2, and the distance between them is, let's say, x. So the question will be like this: find the force per unit length between the two wires. So what do? I'll take the first wire, and because of the first wire, I'll find out what is the magnetic field at the second wire. And if you know, remember this formula, mu naught I by 2 pi r, right? That is the formula for magnetic field created by an infinite wire. So that is the field over here, okay, created by the I1 current. Now to get the direction, you'll have to use right hand rule. Okay, so hold the wire so that the thumb is pointing in the direction of current. Okay, so if you look at the fingers, they're going inwards here and they're coming out here. Okay, so the direction of field is inwards at this point because of I1. That's it. We got the magnetic field. I'm just going to apply this formula. F is equal to, or dF is equal to I into dl bar cross b bar. Okay, so the current in this wire is I2. So I'm going to write I2. So if you just look at the magnitude, it will be simply I2 times dl times mu naught I by 2 pi x. Cross product will also give you sine, but that sine becomes 1 because the angle between field vector and dl vector is 90 degree. Okay, so magnetic field B bar is going inwards, and if you take a small element dl, that is upwards. Okay, so the angle between both of them is 90. That's it. So that is the force df acting on this small element. Okay, and if you actually look at the direction, if you find out the direction of dl bar cross b bar, you can use right hand rule. You will figure out that it is actually in this direction. Okay, that is the direction of df. So the formula that we need to remember is force per unit length. Okay, force per unit length is df by dl. That will be mu naught. This is I1, right? So I'm going to rearrange the terms like this. I'm going to write it as mu naught I1 I2 by 2 pi x. So that is something that you need to remember. Force per unit length. Okay. The other thing that you need to remember is the direction of force. So we have these two wires carrying current in the same direction. If you look at the force that is acting on these two wires, it will be attractive in nature. Okay, when the current is in the same direction, the force is, trying to bind the two wires together. And similarly, if you have this situation where the current is in the opposite direction, then you will see that there will be a repulsive force. Again, the repulsive force per unit length is given by the same formula, mu naught I1 I2 by 2 pi x. So that is something that you need to remember. Now, based on this, we'll do a very, very simple question. So get it right. Let me give you the question like this. You have two infinite wires. And this current is 2 ampere. This current is, let's say, 3 ampere. And the distance between them is, let's say, 2 by pi meter. So tell me, guys, what is the force per unit length? Okay. And you should also tell whether it is attractive or repulsive. Just use the formula and tell me quickly what is the force per unit length. Tell me, guys, quickly. What is the answer?
So that's 6 pi into 10 power minus 7.
6 pi into 10 power minus 7. Attractive or repulsive?
It's attractive.
Attractive. Okay. All you have to do is use the formula mu naught I1 I2 by 2 pi x. Okay, that is force per unit length. So 4 pi into 10 power minus 7, that is mu naught. I1 is 2, I2 is 3, by 2 into pi into x is given as 2 by pi. Well, we just have to cancel this, cancel that also, cancel this 2. So 6 pi into 10 power minus 7 Newton per meter. And the current is in the same direction, so we'll end up getting an attractive force. Okay. Now, the other question I can ask is, what is the force acting on AB, okay, part of the wire? And let me just give 2 points, A and B. So whatever is there between A and B, on that part, what is the force? Okay, so let's say this is given as some 2 meters, let's say. All right, so tell me, guys, what is the force that is acting on that AB part of that wire? How do you find that out? Tell me, someone.
Force per unit length into length.
Yeah, let's say force per unit length multiplied by length of the section AB. Okay, 6 pi into 10 power minus 7 multiplied by 2. So 12 pi into 10 power minus 7 Newton. That's all. Okay, so that's a simple question. So in the exam, in the litmus test or regular PCM test or in the chapter tests, you can expect one such question for sure. So now you know the formula, you know the direction of that force. Please don't make a mistake, get it right. Okay, so let's move on to the next one then. Any questions, guys? Any questions?
So can you go to the previous slide?
Okay. Okay.
Just a minute, sir.
Okay, then you can also take a screenshot if you don't want to copy everything. It's all there in the notes. I'm just revising quickly. Oh, next very important topic from where you get questions is current carrying loop. current carrying loop. So we have a uniform magnetic field. Uniform magnetic field means magnetic field is constant everywhere. Constant in magnitude, constant in direction. So if I draw magnetic field lines, they'll be uniformly spaced. Okay, parallel lines. Okay, so if I place a current carrying loop like this, carrying a current I, if I find out the force, well, net force will be 0 on the wire, guys. Okay, it's actually very easy to derive also. You take a small section dl, find the force acting on it, dl bar cross b bar, and I'd like to find out the net force, so I'll integrate df bar. Okay, that will be that. I and b bar are constants, so I can take I and b out of the integral. And integral dl bar is simply 0. Okay, if you're doing a vector summation of dl bar, right? All these small dl bars of the loop, right? If you add them, okay, you will end up getting a 0 vector. Okay, you start at a point, go around, right? If you add all these small vectors, you're eventually reaching the same point. So the net displacement is 0. Integral dl bar is 0, which means the net force is 0. So that is something that we need to remember. Apart from that, the other thing about this is you'll get questions like these. There is a uniform magnetic field and someone is placing a, let's say, semicircular loop like this. Okay, B is, let's say, 2 Tesla. Semicircular loop is carrying, let's say, 3 ampere of current and the radius is 1 meter, let's say. Okay, so they'll ask you what is the net force acting on the loop. Someone trying to join? Yeah. All right. So what you can do is, again, we'll use the same calculation or same, mathematical computation. So the net force is again I into integral dl bar into d bar. So in this example, dl bar, integral dl bar, right? So if you add all the small dl bars, you'll end up getting a vector which is just starts from this point and goes there. Okay, so that is integral dl bar. So let's say the starting point is A, ending point is B. I can just replace that integral dl bar with the vector AB bar. Okay, so what that means is, if you get a question where there is uniform magnetic field and there is a wire of random shape, it need not be a semicircle also, some random shape like that is there. Okay, you're asked to find the net force acting on it. All you have to do is take the initial point, take the final point, and draw a straight line. Okay, whatever current there is in the wire, just give that much of current to this straight line as well. And ignore that curved wire. Just take the straight line and find the force acting on it. Okay, so let's say the initial point of the wire is P, final point is Q. Then the force acting on that wire is nothing but this. Okay, that is the easier part, right? So in this example, if I have to find out I into AB bar cross B bar, let me first find the magnitude of the force. Okay, that will be I into AB into the magnetic field into sine of angle between, AB bar and the magnetic field B bar is 90 here. Okay, it's 90, so good, sine 90. So current is 3 ampere. AB, which is the distance between the 2 points A and B, right? That is nothing but the diameter. Okay, and the diameter is given as radius is given as 1 meter. Diameter is 2 meters. Okay, that is the length AB, and magnetic field is also given as 2 Tesla, and sine 90 is 1. So that is 12 Newton. So whenever you have a current carrying wire placed in a uniform magnetic field. Don't worry about the shape of the wire. Just join the ends. Okay, make it straight wire and find the force. That will give you the answer. So that is about the force acting on a current carrying wire placed in a uniform magnetic field. All right, now let's come back to the current carrying loop now. We found out the net force is 0. Okay. Now the next formula that you need to know about this is the net torque. So torque acting on a current carrying loop placed in a uniform magnetic field. Okay, so I'm not going to prove it here. I'll just show you how you will get a formula and how to use it. So the torque acting on a current carrying loop is I into A bar cross B bar. Now what is A bar? Area of the loop. Area of the loop means this area, right? But the thing is A bar, right? A is a vector. It's A bar. It's not just A. So what is the direction of area? Okay, so to get the direction of area, we use right hand rule. So current is going anti-clockwise here. Okay, so if you curl the fingers of your right hand in the anti-clockwise direction, the thumb will be pointing out of the screen. Okay, so if you curl your fingers in the anti-clockwise direction, thumb will be coming out of the screen. So the direction of area vector is outwards. Okay, so if this is the loop, current is coming out, the current is going in the anti-clockwise direction, area vector is outwards. Okay. Similarly, if you have a loop where the current is going clockwise, let's say, okay, then the area vector of the loop, oh wait, outwards, right here. So outwards means you'll have to put a dot. Right, so if the current is going clockwise, then the area vector is inwards. Okay, so if you turn the fingers of your right hand in the clockwise direction, the thumb will be pointing inwards, right? So that's it. That is the direction of area vector. Okay, so once you get the area vector, all you have to do is find out I into A bar plus B bar. That is going to give you the torque acting on the loop. Okay, so a very, very simple question can be something like this. There is a magnetic field which is 3 Tesla, and there is a circular loop carrying a current of 2 ampere in the anti-clockwise direction. Now the radius is let's say 1 meter. Okay, find the force. That is the first part. Next part is find the torque. Now force, well, can you guys tell me what is the force acting on this loop?
Sir, 0.
0. We have already seen that. Net force acting on a current carrying loop placed in a uniform magnetic field is 0. That was our previous slide. Well, over here, I'll simply use the formula. Torque is equal to I into A bar cross B bar. Now, the important part over here is to decide what is the direction of area vector. So tell me, guys, area vector in this case is outwards or inwards?
Outwards.
Outwards. You just look at this. Okay. According to the right hand rule, curl your fingers in the anti-clockwise direction. Thumb is pointing outwards. So that's it. That's the direction of area vector. So it is area vector is pointing outwards, right? Which means I have to draw it like that. That is the direction of area vector. So, you know, it's making an angle of 90 with the magnetic field. So if you see the magnitude of the torque, it will be simply IAB sine 90. Okay, that is 2 into area is pi r square, pi into 1 square. Magnetic field is 3 Tesla, sine 90 is 1. So that's it, 6 pi Newton meter. Okay, that's how you find the torque. Now, the question won't stop there. They'll also ask you, what is the direction of torque? Okay, direction of torque, if you look at A bar cross B bar, you have A bar coming out of the plane and B bar going towards right. So if you use right hand rule, okay, if you use right hand rule, you'll end up getting the direction to be upwards. Okay, now unless you practice it, unless you do it on your own, it's going to be difficult for you. Okay, find out A bar cross B bar. You should be very good with finding the direction of cross product of two vectors. Okay, so right now it's difficult for me to show how A bar cross B bar is upwards, but all I say is use the right hand, place it along area vector, curl the fingers towards magnetic field vector. The thumb will give you the direction of A bar cross B bar. Okay, and here it turns out to be upwards. So the torque is in that direction and it is equal to 6 pi Newton meter. Now, torque is in the upward direction. What does that mean? Like, how is that going to rotate the body? Well, we know torque rotates the body, right? And if I say torque is upwards, what does that mean? Does it mean the body is going to rotate upwards? Doesn't make any sense. What is rotating upwards, right? Well, torque being upwards simply means the body is going to rotate. Well, again, you have to use right hand rule. Okay, torque being upwards, that is the direction of torque, right? It simply means the ring is going to rotate like this. Okay, so it's going to rotate like this. That's how the torque is going to rotate. Okay, so that's what direction of torque means. If the direction of torque is upwards, it doesn't mean the body is rotating upwards, right? It doesn't make sense. Okay, you have to use right hand rule. So point the thumb in the direction of torque and see how your fingers are curling. Okay, however your fingers are curling, that's how the body is trying to rotate. Okay, or the torque is trying to rotate the body. So that's it, guys. That's how the torque is being applied on the body. Okay, so we have seen net force, we have seen net torque. Okay, now if you look at the formulas, right? If you look at the formula for torque, it is I into A bar cross B bar. If you look at the net force, it is 0. Okay, now you should be noticing a similarity between this and an electric dipole. If you take an electric dipole plus Q and minus Q, place it in an electric field, a uniform electric field. Okay, if you remember, there also net force is 0, torque was P bar cross E bar, where P bar was the dipole moment. Okay, so if you look at these two formulas, it's I into A bar is kind of acting similar to E bar here. Okay, we've got it down. Yes, Janvi? You raised your hand?
Sir, in all these questions, we assume the loop to be in the plane of the paper, right?
Yeah, but it doesn't matter. The loop can win anyway. Based on that, your area vector will get decided.
Yeah, so according to that, we can put the angle and everything.
Yes, yes. Okay, so it need not be in the plane of the paper. It can be in any plane. In fact, the loop need not be in a single plane, right? Loop can be a 3D loop, which can be in multiple planes. So if you remember, we kind of break it into two different planar loops.
Yes, sir.
Yeah. Okay. Anyway, so to keep it simple here, torque is I into A bar cross B bar in the case of a current carrying loop, and it is P bar cross E bar in the case of electric dipole. So we saw these similarities, and then we said, hey, you know what? Let's take this current carrying loop, and let's just assume it as a dipole. Let's say it is a dipole. Now, this dipole is not an electric dipole because it is reacting to magnetic field, not electric field. So we said, okay, let's call this as a magnetic dipole. All right, I'm going to call it as magnetic dipole. Then what is this dipole moment? Well, compare the formulas. This is similar to this. So I'll say the magnetic dipole moment given by m bar is simply I into A bar. Okay, what is this? Magnetic dipole moment. Instead of saying magnetic dipole moment, we simply call it as magnetic moment. Okay, so we're going to consider current carrying loop as a dipole. What dipole? It's a magnetic dipole which reacts to magnetic fields. And what is the dipole moment of the dipole? Or, what is the magnetic moment of the dipole? It is I into A bar. Okay, where A bar is the area vector of the loop. Right. So this is how we consider current carrying loop as a magnetic dipole. Now, if you look at, if you remember electric dipole, there was another formula that we learned. It is the potential energy. Okay, we say minus P bar dot E bar. Here also I can do the same thing. Okay, minus M bar minus M bar dot B bar. Same formula. In fact, if you look at the proof, it will be exactly the same. Just replace E with B and P with M, and everything looks the same. Okay, so for example, you'll get a question. So you'll have this, and there is a loop like this. Okay, it's carrying current like this, and magnetic field is, let's say, 2 Tesla. And area of this loop, let me just give the area directly. It's let's say 5 centimeter square. And the current the loop is carrying is 1 ampere. Now the question can be like this. Okay, first of all, what is the torque what is the force acting on the loop? Well, we know it's simply 0. Net force is 0 if it is placed in a uniform magnetic field. Next question is, what is the torque? Can anybody tell me?
Also 0.
Yeah, very good. M bar cross B bar. Okay, M bar is I A bar, right? So I A bar cross B bar. Now, if you look at the diagram, the direction of A bar is also along the magnetic field. Okay, if you use right hand rule, you'll figure out that if you curl your fingers in the direction of current, the thumb will be pointing towards right. Okay, so area vector is towards right. Magnetic field is also towards right. So they're in the same direction. Cross product will simply become 0. Okay, the angle between them is 0. So sine 0 is 0. The next question is, if I am trying to rotate, okay, let me just draw it here. Yeah. If I'm rotating the ring along this axis, okay, along that axis, I'm rotating the ring like this. Okay, by how many degrees? 90 degrees. What is the work done? Okay, what is the work done to rotate the ring by 90 degrees? Okay, as shown in the figure. Well, all I have to do is find the change in potential energy. P initial is minus M bar dot B bar. And if you look at the initial angle, it is 0. So minus MB cos 0. Okay, P final. Well, finally, the angle between both of them is 90 degree, which means minus MB cos 90. And that is 0. Okay, let's also find this minus MB cos 0. So minus M is I into A, right? So I into A into B. So if you look at the work done, well, all we have to say is work done by the external force is getting stored as potential energy in the current carrying loop. Okay, work done is nothing but the change in potential energy. So whatever work we are putting into rotate, it's all becoming potential energy. Okay, we are assuming that we are slowly rotating it, which means kinetic energy is negligible. We are slowly rotating it. So whatever work we are doing in is just becoming potential energy. So change in potential energy is P final minus P initial. That's it. It will be IAB. Everything is given, right? I is 1 ampere. Area is 5 centimeters square. So obviously, you will have to convert that into proper units. 5 centimeters square is 5 into 10 power 4 meters square. Into magnetic field is 2 Tesla. So 10 into 10 power minus 4 joules, right? It's 10 power minus 3 joules or 1 millijoule. That's it. So that's how we can find out the torque and also potential energy. Using that, we can also find out work done. Okay, all these questions can be asked. So we have a few more minutes. Okay, we have a few more minutes, sir. We'll just look at one last topic. Hmm.
Sir,
Yeah, yes.
sir, we said that we can't define potential in magnetic field, right? Since it was non-conservative. So
Yes, yes, yes. So in this
um,
regard, we can actually do it as long as you don't displace the loop, as long as you just keep rotating it, okay, by fixing its center of mass. In that context, you will see that it behaves like a conservative force. It behaves like. So you can define potential energy as long as you don't move it, okay? If you just keep it rotating about the fixed axis, it's okay. Okay.
okay, so like only for rotation we can, but like if there's any translation motion, we can't do that.
No, no,
Then
we shouldn't be doing it. Okay.
okay.
I mean, we can still find out work done and all that, but we shouldn't use the word potential energy. Okay.
Okay, yeah, got it. Thank you.
Yeah. Okay. One second, one second. Okay. So, yeah, 5 more minutes. Let's look at something else. So, current carrying wire, we have seen how what happens to it when you place it in a magnetic field. But now what we're going to do is we're going to see how much of magnetic field will this current carrying loop create. Okay, so if you have an electric dipole, let me just draw an electric dipole here. Right, I'd like to find out the electric field here, right, at a point which is at a distance r from the center of the dipole and makes an angle theta. So we define two components, ER and E theta. Well, this is 2 kp cos theta by r cube, and this is kp sine theta by r cube. Now, in the case of magnetic dipole, right? Magnetic dipole. What is magnetic dipole? Magnetic dipole really doesn't exist, right? It's just current carrying loop. We treat it, we look at it as a magnetic dipole. So there is a loop like this. Okay, it need not be circular. It can be any loop. All right. Area of the loop is, let's say, A. So if someone asks you how to find out, or if somebody asks you what is the magnetic field there, you might have seen this formula, right? Formula for magnetic field on the axis. But the sad thing is, this is not an axis. We are not looking at a point that is on the axis, right? Axis is like this. So this point is not on the axis, right? So we cannot use any of the formulas that we know. But good thing is, we have seen that this current carrying loop acts like a magnetic dipole. Okay, which means I can use the formulas that I've learned in the case of electric dipole. Okay, so those formulas can be used under the condition that R is very, very large compared to the radius of the ring. Okay, as long as R is very large compared to the size of the current carrying loop, you can always consider it as a dipole and use the formulas for electric dipole. Okay, so let me show you those formulas. So here we have BR and B theta. That's a very easy, right? You know, you look at these, look at this, and just write a similar one. So 2 is there, so I write 2. K. K in the case of electrostatics is this, right? So here, we write it as mu naught by 4 pi. Okay, so instead of 1 by 4 pi epsilon naught, it is mu naught by 4 pi. And then we have a P here. P is the dipole moment, electric dipole moment. Here it is the magnetic moment, M. And what is M? I into A. Okay, vectorially it is I into A bar. That's it. Everything else is same, cos theta by R cube. And B theta is also mu naught by 4 pi M sine theta by R cube. That's it, guys. All right, you just have to remember these. And, sometimes they'll ask you, what is the field over here? Okay, so this point is again quite far. Okay, this is R, which is very, very large compared to R. In that case, again, we can use the formulas BR and B theta. So BR mu naught M by 4 by cos theta. Theta for this point is 0, right? Okay, this is your R vector. You can see it's making an angle of 0. So it will simply be cos 0 by R cube. So 2 mu naught M by 4 pi R cube. Similarly, we have B theta. And that is mu naught by 4 pi. You have a sign there. Okay, M into sine 0 by R cube. Well, sine 0 is 0. Good for us. It's going to become 0. Okay, so that's how you find the field. This is the axial line. Okay, so the formula for field on the axial line due to a current carrying loop is this. Okay, where M is I into A bar. Lastly, I can also ask you what is the field somewhere over here. Okay, again at a distance R from the center. Now, again, all you have to do is use the formulas for BR and B theta. So BR has cos theta term, right? And for this, theta is 90 degree. Okay, so BR is going to become 0 because cos 90 is 0. And B theta, well, mu naught M. Sine theta is there here. So sine 90 is simply 1. So we just have mu naught M by 4 pi R cube. That's it. Okay. So what do you need to remember here? You need to remember formulas for BR and B theta. If you know those two, you can easily write down the formulas for field on the axial line and equatorial line. Okay, so that is it, guys. That's how we treat a current carrying loop. So we have two things here. Firstly, we have seen how it reacts when it is placed in a uniform magnetic field. We have seen what is net force, what is torque, what is potential energy. Next part of it is we have seen what magnetic field it creates. Okay, how much magnetic field this current carrying loop creates. So for that, again, we have two formulas, BR, B theta. Using that, you can also find out field on the axial line and field on the equatorial line. Okay, so sometimes a loop will have so many turns. Okay, this is a single turn, but what they do sometimes is they'll take a wire and make two turns out of it, let's say. Then magnetic moment will be I into A bar cross, sorry, I into A bar is the general formula, but since we have two turns, you have to multiply a 2 there. If you have n turns, then it will be n into I into A bar. That's it. Okay. So that's it, guys. I could have given a simple question, but it's already 9 o'clock, so I'm gonna leave you guys here. So thank you for attending. If you have any questions, you can just stay back and get them clarified.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.